Thank you so much for having me. It's been an honor to be invited to honor the memory of Robert. I've been reading a lot about his life, and of course, talking to Juliana, I realized how incredible of a scientist he is, but how incredible of a human being he was. So it's been really inspiring. I have to say that this is the photo I have as a Niels Bohr professor in one of the corridors outside my office when Niels Bohr actually visited Caltech, and you can clearly see there Robert in the photo. I realized that we have some things in common. We were both at Los Alamos, and we were foreigners, so we had these red badges that indicated that we were not U.S. citizens. As you know, he actually did a lot of his astrophysics work at the Institute for Advanced Study when I was there for 4 years, and was also a sabbatical at Cambridge, where I did my PhD. I didn't, of course, have the opportunity to meet him, but it's really an honor to be given the opportunity to talk to you about this, which is also, intimately related to. Robert was really the pioneer in thinking about radiation hydrodynamics, and it's a tool that we use a lot today, and it's basically a key point of what I'm going to tell you today. So I'm going to tell you about Nutristore mergers and their ability to produce R-process elements. I want to just highlight this is work that I've been done in collaboration with a lot of my students and postdocs, and a lot of the work I'm going to present has been done in close collaboration with Dan Kaysen, who's a professor at Berkeley, but he was a postdoc at Santa Cruz, and we worked together on this topic for a long time. So this is the outline of my talk. I'm going to define what the R process is. I'm going to guide you through the nuclear properties and describe what the R process is. I'll tell you as astronomers, what do we know about the R process? What are the observational constraints on the R process? And then I'll dive into Nutristore mergers as a side of R process nucleosynthesis, and particularly trying to give you a feeling of, after a Nutristore merger, what are sort of the telltale evidence that we can infer that, in fact, these R process elements were produced as a result of the merger and were ejected? Yeah. So, in particular, talking about the light curves and spectra. And of course, we were incredibly lucky on 170817, where we actually detected the electromagnetic signature. So I'll go into detail how, in fact, a lot of the predictive work that we did in advance actually matched relatively well with the observational properties of this event. But I'll tell you about some of the challenges that we're now facing to really trying to understand in detail. Juliana is very familiar with this. She's done a lot of seminal work on nucleosynthesis, but the majority of clues that we have about nucleosynthesis, particularly of heavy elements, comes from spectroscopic resolutions, high resolution spectroscopy of the sun. Yeah? And a lot of work has gone from going through these beautiful spectra to really look at the abundance pattern of the sun. Yeah? So for astronomers, this is our periodic table. Yeah? And there's a huge amount of very interesting information encoded in this pattern. The first thing that you notice is, of course, the odd-even asymmetries that clearly correlate with abundances, and we'll talk a little bit about that. But more importantly is the abundance correlating with these close neutron and proton shells. Yeah? You clearly see that the abundance peak of iron is in this magic number 28. And there's two interesting things that happen. One, of course, is that the number of neutrons that give stability increases as a function of atomic number. You can clearly see you have a doubly magical lead, which has N of 82, N of 126, and Z of 82. And what I really want to focus are on these peaks, this peak, which appear not to, at first sight, be related to nuclear structure, and those are the R process peaks. Yeah? And what I'm going to tell you is that, indeed, they codify nuclear structure, but because they're captured far away from equilibrium, the peaks are actually appear moved in position. So I'll talk about how this pattern actually emerges. So the vast majority of elements above iron are actually produced by neutron capture. Astronomers are not very inventive, but we call S process slow capture of neutrons. So you capture a neutron and you beta decay, and then the time scale for the next capture is long compared to the decay, and we call that slow. if the time scale between capture is faster than the decay, that's what we call the R process. Yeah? And hopefully I'll give you some pedagogical introduction as to how are these abundance patterns actually emerge from nuclear structure. And of course, the two reasons why neutrons are required is, of course, that as you go, iron is the most bound nuclei in the cosmos, and therefore, if you want to produce elements above that, you have to give energy to the system. So those reactions are actually do not produce heat, but in fact take up heat. But the most important constraint is, of course, that the Coulomb barrier increases with atomic number, and then charge reactions are really not effective in producing the heavier elements, and you have to rely on neutrons. Okay, so I'm going to spend a little bit of time in this. I'm going to move in front. It's, I think, a little bit easy to point. But what you're seeing here is proton number as a function of neutron number. This is from the review of Chris Needham. Just to remind you, if you capture a neutron, you move in this direction, and you beta decay. The first thing to notice is where the stable nuclei are. So these are the black nuclei here. So that means that if you're close to the S process, you're very close to the value of stability. That means that the S process actually arrives here. You capture a neutron, you beta decay, and you move through the valley of stability. Okay? Another important thing to keep in mind is that as you move away from the valley of stability, the beta time scales becomes progressively shorter. Okay? The lifetime of this nuclei is actually relatively short when you're far away from equilibrium, and this is important. Another thing to keep in mind, these are the limits of experimental data. So a lot of what I'm going to talk to you a lot about the R process, which you can see here, one of the trajectories, happens far away from where we have actually observational data. So we use a lot of inference of models in order to understand the capture. So this is sort of a separation energy of about MeV, a few MeV. This is an R process pathway. And what you immediately notice is that the R process has to happen incredibly far away from stability. Looking at the beta decay timescales, you realize that the entire capture has to be over in tens of milliseconds. And then, the natural conclusion is, what is the only object in astrophysics that has a dynamical timescale of that order? Well, it's a neutron star. Yeah? And therefore, the two sides of our process nucleosynthesis is either when a neutron star is actually born or when two neutron stars merge. Yeah? So that timescale naturally kind of defines the astrophysical origin, and we'll talk a little bit more about that. Another thing that you see here is the closed neutron shells and, of course, proton shells, but these define basically the abundance patterns of the R process. Yeah? So I'll tell you why. As you can see, you have 2, 8. These are the so-called magic numbers, and something very interesting happens to the flow of neutrons when they arrive to that magic number. And the case is that I'm showing you here just as an example the neutron capture cross-section on the S process path with neutron energies of about 25 kiloelectron volts. And the things that you see are incredibly telling. The first thing that you realize is that odd mass numbers tend to have higher cross-section than even nuclei. But the thing that it's mesmerizing is the substantial lowering of the cross-section near the magic numbers. And that makes perfect sense. These nuclei do not want to capture neutrons because they are stable. Yeah? And you want to move them far from stability, and they don't like that. So the way that I understand the R process production is you can think of it as neutrons, that you have a neutron flow, and as soon as they get to the magic number, you get stagnation of the flow, and what that happens is that the abundance starts increasing. It's sort of, I guess, cars in a highway. If you have a collision, then you get a pileup. So not surprising, abundance anti-correlate with neutron capture cross-sections. And that starts giving you a feeling of how these abundance peaks actually come to light. So what happens is you're capturing relatively far from stability. You stagnate here. You get a significant abundance peak. You continue. You stagnate. You continue and stagnate. So there's 3 characteristic peaks in the abundance pattern, 1, 2, and 3. Now, of course, if you compare that with the peaks of the S process, which happen here, 1, 2, and 3, that means that the entire our process pathway, by the time they decay back to stability, you're seeing the projection of this plane out into the stable nuclei, and the 3 peaks move to the left. Yeah? So naively, what you think that they didn't really correlate with nuclear stability, in fact, they do. Yeah? But what happens is that they are captured so far away from stability that by the time they decay, these peaks are basically shifted. And that gives you an idea of how this abundance pattern emerges. And something to keep in mind is that about half of the elements above iron are produced by the S process, and half of the elements are produced by the R process. And not particular element is either produced by one or the other. You can see, for example, lead here has contributions from both. You can see my favorite peak of R process here. You can kind of know why, gold and platinum. And those are almost exclusively made by the R process. Europium is a particular important nuclei because it has a very high oscillation strength, so it produces a feature in the spectrum that is actually relatively steep, and we can actually, so we use europium as a telltale of the R process contents of stars, atomically speaking. And we use barium in many cases of a telltale of S process signature in the stars. But of course, there's some arguments as to why barium, particularly in the early universe, can be used for R process because the S process takes a significant amount of time to appear in the universe. So if you really like stars with relatively high abundance of gold, this should be your favorite star, which we call the Chris-Nidden star because Chris-Nidden characterized it. And what we have really learned from our process observations is something that is incredibly strong, which is that the abundance pattern of the R process is extremely robust. So what you show here are a large fraction of low metallicity stars that have very high resolution spectra, and superimposed is actually the R process abundance pattern of the sun. Yeah? And of course, they're being changed in normalization. So the amount of gold from star to star can vary drastically, but the abundance patterns, the relative ratios of elements between the second and third peak is extremely robust. And therefore, you have to conclude that whatever process is has operated incredibly robustly since the beginnings of the universe. Why? Because these stars are extremely low metallicity, and as a result, they're also some of the oldest stars in the Milky Way. Okay. Another important telltale in observations is that there's significant amount of variations of the R process content from star to star, particularly at low metallicity. So this is iron abundance in logarithmic scales, and this is europium to iron. And what I'm going to show you is, for example, 2 stars that have similar iron abundance, but whose R process content or gold content can change by almost 2 orders of magnitude, if not more. Yeah? And when you look at the RMS fluctuations of other elements, it's significantly smaller than that of europium. Yeah? And I'll tell you a little bit more about this in my talk. Another interesting thing is that only a few % of these metal-poor and all stars actually show clear R process signatures. So this is already hinting to an enrichment process that it's rare. Yeah? The way that I like to think about this is if you think about type 2 enrichment, so type 2s are very common. You can think of it as a chocolate cookie with a very thin layer of chocolate, where the chocolate is very well distributed. When you think about our process enrichment, you can think about a chocolate chip cookie. So if you're very, very close to the chocolate chip, you will have a huge amount of our process, and if you happen to, to be born far away, you have very little. So there's basically extreme variations in the content, in the gas content of our process in the early universe. And you can see these clearly. For example, if we look at the calcium features, 2 stars have very similar calcium features. But if you look at europium, look at the difference in content. So this star is significantly enhanced in our process compared to the red star here. So a good number to have in mind is that in the Milky Way, on average, over the history of the universe, you're producing about 1 solar mass per year. Yeah? So every time on your birthday, on average, you have a star like our sun coming to life in the Milky Way. Yeah? That's more or less the star formation rate of the Milky Way. With that star formation rate, you need about 10 to the minus 7 solar masses per year of our process. Yeah? So if you want to explain the R process content, which is locked up in the stars today in the Milky Way, that's the rate of mass production that you require in the universe, okay, on average. So the two most widely discussed scenarios is the core collapse process, especially after the shock has break through and you have these neutrino-driven wind, or neutron star mergers. So if you remember these magical 10 to the minus 7, core collapse supernova happen about once every 100 years, so 10 to the minus 2. So the mass per event requirement there has to be about 10 to the minus 5 solar masses. While neutron star mergers happen about once every 100,000 years, so 10 to the minus 5. So you need a production rate of about 10 to the minus 2 solar masses. Yeah? And these were sort of the numbers that were put forward for many, many years, saying, these are sort of the requirements that we need in order to explain our process nucleosynthesis in the universe. Now, there's actually a relatively simple estimate that you can make when you look at the abundance of particular stars, and you say, well, after a neutron star merger or a supernova, I have a blast wave. The blast wave is actually hot, so I cannot convert that material into stars, and I have to wait until it sweeps enough mass that it cools. And once that cools, that gives you a minimum mass before you can turn that gas into stars. Yeah? So the argument is you have to sweep of the order of about 10 to the 3, 10 to the 4 solar masses of gas. That, of course, depends on metallicity and the energy of the explosion before you can actually turn that gas into stars. Now, the argument is, of course, that blast wave or that explosion produces a certain amount of our process. Yeah? So when you look particularly at the europium to hydrogen ratio, you can derive what is the minimum amount of mass a single explosion has to make in order to explain the enhancement that they see in the stars. And this is derived very elegantly here by Phil Macias. And what you can see is stars that are drastically enhanced in europium require a mass per event, a minimum mass per event of about 10 to the minus 3 solar masses. Yeah? And remember, the core collapse constraint, which is about 10 to the minus 5 solar masses, fails to basically enrich these stars with enough our process material. Yeah? So what we initially think is that the standard core collapse supernova cannot work, and that means that the R process has to be produced by a rare event which produces a significant amount of mass per event. And these constraints are incredibly solid and give you a simple estimate for the minimum mass that you need of R process. So you can conclude that the production of heavy R process elements, and by heavy people usually refer to the second and third peak, because that is where the observations tells you that the pattern is extremely robust, has to operate robustly and at a drastically reduced rate when compared to core collapse supernova. Yeah? So again, this idea of the chocolate chip cookie versus the chocolate being very, very effectively mixed, that's how we think of our process enrichment in the early universe. Yeah? There were very, very few of these events, but they produce significant amount of mass per event. And that's a constraint. So if we're going to talk about neutron star mergers, how is the R process made? And here I'm going to tell you about the simplest, most robust mechanism to make the R process. And then at the end of my talk, I'll argue that there are other avenues to make it during the merger. And I'm going to talk about the tidal tail ejection. So what I'm showing you here is actually a very old simulation when I was a grad student. Just as an illustrative process, it was not full GR. But ultimately, you have two neutron stars. They become dynamically unstable. You get mass shredding in the outer Lagrangian points. About 1% of a solar mass is actually ejected above the escape velocity and expands. This material is actually not irradiated by neutrinos. It's extremely neutron-rich, and we believe that that is an ideal site for the R process. Yeah? These tidal tails expand, escape, and as I will show you, produce a very, very robust R process pattern, particularly in the second and third peak. Since then, there's been a huge amount of work done in relativistic hydrodynamics, including magnetic fields, different equation of states, different mass ratios. The sort of convergence is that the mass ejection in these tidal tails varies between 10 to the minus 3 solar masses to 10 to the minus 2 solar masses, and it moves at velocities of a fraction of the speed of light. And that depends exactly on where the outer Lagrangian points lie. So what I'm going to show you here is calculations with an hour process network that includes neutron captures, photodissociations, alpha and beta decay fission reactions. But the reason why we spend some time looking at that plot is to try to understand the trajectory. So here again, we have protons, neutrons. What you're going to see here is the abundance pattern as a function of time. We have YE, which is the electron fraction, which is how neutron-rich the material is. 0.5, of course, is equal number of neutrons and protons. We have entropy, density, temperature, illustrated by this as a function of time. So what happens? In nuclear statistical equilibrium at these conditions, you have free neutrons, but you also have ions. So you basically have already the targets ready to be captured. Yeah? And this is one of the huge advantages that we have at really neutron-rich material, that at nuclear statistical equilibrium, we both have tons of neutrons, but we already have the nuclei to capture those neutrons. So what you're going to see is a movie as a function of time. You clearly see the stagnation points in the magic numbers very, very quickly, and then the decay back to stability. And as you can see clearly, the three peaks, first, second, and third, and you saw them move as a function of time when they were basically captured out in equilibrium and decay. Now, something that is incredibly important for the tail I'm going to tell you is that these nuclei continue to decay and produce an extensive heating rate as a function of time. And this is the heating rate which we believe intrinsically heats up the material as it expands, keeps it from adiabatically cooling, and produce an electromagnetic transient. So gold, you can ask, how much gold, which is about 6% of the total mass of our process, was produced in one of these events. This is, of course, for Mike, and it's about a Jupiter mass of pure gold made in a neutron-star merger. If that's not impressive enough, it's also the amount of gold stored in about 1 million stars. So again, it hints to this argument that our processes are made by this extremely rare event, but it produces so much that it can actually supply significant amount of it has to supply a significant amount of our process to a very, very large fraction of stars. And it also intrinsically explains why we have so much RMS variation of the gold content in stars, particularly in the early universe, where mixing was not as efficient. So you can think of neutron-star mergers expanding a secular evolution phase, which lasts a gigayear. We see many of them because one of them is a pulsar. We know that they're going to merge in less than a Hubble time. In this particular tail that I'm telling you, you have basically dynamical instability, the ejection of material in the outer Lagrangian points. That lasts a few milliseconds. You have basically our process production happening very, very fast. And what matters here is what is the energy and mass content of the unbound debris. What ends up happening? Well, you have both expansion and nuclear heating of the outflow. So this nuclear heating is basically being captured because you're optically thick. The energy is being degraded. And the energy comes out when the material becomes optically thin, which in this particular case happens at about few AU. So the key questions that we had in mind is how does the light curves look like? What are the telltale signatures of our process? And what can we say about the spectra? And remember, this is a ball of our process material, and you can think about the atomic structure of these elements, which, of course, are high C number, but as I will show you, it's not the number of electrons that matter, but the atomic complexity. And these atoms are incredibly complex. Okay, so these are some calculations pioneered by Luke Roberts, who was a grad student working with me at UC Santa Cruz. And what you see here is the nuclear decay as a function of time. And what's telling is it is a power law, which was actually predicted by Liam Paczynski. And it is a power law because this is the contribution of a particular element, and you have so many elements contribute to the nuclear decay at every given time. And naturally, you get this sort of power law heating rate. Yeah, so when we talked about sort of the work that Robert has been doing, Pioneer is very similar here. We have a radiation-dominated compact ball. It's basically expanding, so you have adiabatic cooling. You have radiation leaking out, so that depends very strongly on the opacity, and you have a heating rate that basically fights for the internal energy not to be depleted. Okay? So you expect, naturally, that the bolometric luminosity should know something about the energy injection rate, and that's one, at least, of the telltale signatures that we think are essential. I put this because I found it quite interesting. This is the radioactive heating in the solar system based on the abundance pattern of the solar system. And again, you have contributions for a large fraction of elements, very similar to what we're seeing here in our process. If you're particularly interested on late time heating in the solar system, you have to actually look at something like uranium and thorium, which are our process elements. Yeah? So for some of our planetary science colleagues, there's been significant amount of discussion lately that the uranium and thorium content from actually even in solar metallicity stars can actually change by a factor of 5. So how does planetary internal structure changes when the internal heating rate of a planet could actually change by a factor of 4 or 5? Is the dynamo that creates the magnetic field operating effectively or not? Is our process something that we have to worry about when we think about the Drake equation? Yeah? Is the our process content of a planetary system something that will determine habitability? And potassium, of course, is also a very important contributor. Okay, so when we think about type 1a supernova, of course, type 1a supernova are primarily powered by the decay of nickel into cobalt and then into iron. And you can clearly see here the heating rate. And basically, the luminosity grows, and the object becomes optically thin, reaches a peak, and then follows the radioactive decay. These models were known by the Berkeley group as kilonova models because their luminosity is 1,000 times that of novae. And you can see here, this is the predictive heating rate. And we see that, on average, we expect the LIGO to actually follow the heating rate. And you can see that, of course, the total luminosity and duration depends strongly on the amount of mass that you produce, from 10 to the minus 2 to 3 times 10 to the minus 2. Now, it's an interesting historical tale that, of course, when supernovae were first found, it was, people were desperately looking for energy injection on timescales of 55 days, and the element californium seemed to actually do the trick. So this was supernova in californium-254, and as you can see, Robert played a central role in that. And of course, in this particular case, there's only one element that is doing the decay, and in our process, you have this large number of simultaneous decay that are doing the heating rate. So we had an idea about the energy injection rate of these systems, and we had to think very carefully about the opacities. Yeah? And I just want to highlight our ignorance that there's really limited experimental line data, and in order to understand the atomic structure of our process elements, we require atomic structure modeling, which is actually not currently available. So Dan Kaysen at Berkeley made some relatively simple arguments that I think carry a huge amount of impact in the field. And he says, well, let's think about the atomic complexity of these atoms. And as you know, atomic complexity is not related to the number of electrons, but really the way that you can distribute the valence electrons in the open shells. So in particular, these F-shell nuclei should have a very, very large fraction of line features. Yeah? So the majority of the opacity in our process should come from these series. And to illustrate this, in this seminal paper in 2013, Dan plotted the complexity of the elements, and by atomic complexity, he said the combinatory ways in which you can arrange these valence electrons in the open shells. And you can see here for S, P, D, and F orbital angular momentums, and you can see the F shell carries a significant fraction of complexity, which immediately tells you that there's going to have a significant fraction of line features. Yeah? And this is the abundance pattern from one of our calculations. So these elements sit between the second and third peak, which means that whatever produces them has to act incredibly robustly, because we know that from observations. So let me show you sort of the calculations, the statistical calculations in which you try to put lines in a statistical way for iron and other elements, some of them in the F shell, some of them in the D shell. So Dan did this, and what you see is basically the opacity of the D shell is, of course, much, much, much smaller than the opacity of lanthanide, of these F shell nuclei. So the argument was, if you look at the opacities, that these transients are going to be extremely red. You're going to have to move from the optical into the infrared in order for radiation to escape, because the opacity was very, very large. And that was a very, very important prediction for our field. So let me show you the results of this. If you take our process elements with very little material between the second and third peak, then you get a relatively blue optical spectra. And if you take something that has significant amount of lanthanide, you actually get a significantly reddened spectra. Now, of course, for astronomy, this is not good because it's significantly more difficult to detect this than it is to detect in the optical, since detectors are significantly more efficient at optical wavelengths. So this is about the model spectrum of about 4.5 days after the merger. Now, something that it's challenging but also important is that these line features are broadened because the entire system is moving at a fraction of the speed of light. Yeah? So the structure of the spectrum, as you can see, drastically changed depending on the outward velocity of the material. So there's also a spectral determination of the ejective velocity by just looking at the intrinsic broadening of these line features. Now, when we talked about line features, we're not talking about a specific lines, but an agglomerate of lines. Yeah? So a lot of work has to be done to really try to understand, do we see particular edges that we know the rest mass, the lab rest frequency, so that we can actually detect whether or not the material is coming towards us or away from us, whether or not we have one or two tails, which depends also on the mass ratio. So one of my favorite days, I think after the birth of my two children, was August 17, 2017. I don't think in this audience I have to tell you about this event. I think it's part of your DNA. But what happens was basically try to find out the electromagnetic counterparts, and we were aided by the fact that Virgo had just turned on, and the position in the sky was actually significantly reduced compared to others. And we are hoping LIGO continues to provide such small error bars in the sky, but it hasn't really happened. I'm part of the collaboration, which is called the 1 Meter Two Hemispheres. This is a collaboration that got together the year before. We have two 1 meter telescopes. One is LIGO Observatory, very close to UC Santa Cruz, and the other one is in Chile, the SWAP telescope, which is a 1 meter telescope. And I just wanted to highlight Ryan Foley, who's the PI, who had moved to Santa Cruz a year before the event. David Coulter, who's the first author on the discovery paper. He was actually a software engineer, first generation college students from a Hispanic background. This was his first project, and he actually maximized the algorithm to try to maximize the number of galaxies that we were doing in every pointing, and then try to put an algorithm to basically say, which galaxy should we point and in what order depending on their probability. Because, of course, we had a 1 meter telescope and we were competing with 4 meter telescope. And Charlie Kilpatrick, which is the first person of human history to actually see a photon associated with a gravitational wave. So he detected the first photon in the image, and there's some really interesting Slack communication that for this audience I will spare you the details of the profanity of language, of excitement when this was detected. Incredibly proud of our UC Santa Cruz team, incredibly proud to the fact that I'm the oldest person in that photo. And we have an incredibly diverse team. And something else that Ryan and I are incredibly proud is that every single paper coming from our collaboration was actually led by a grad student or a postdoc. So this was the SWOP telescope. This event, if it was actually looked up in Africa, they would have detected it first, but we have to wait until it was dark in Chile to actually see it, and we basically detected the first photon. So something that was, and this is Dave's Coulter paper, so something that is incredibly interesting here was that the source was extremely blue early on, but then it turned red. And as you know, the argument was that the R process opacity of these elements was going to basically be so high that the light was going to escape, in the infrared. So that was interesting, and we'll talk a little bit about the blue component. So what are the lessons that we have learned? This is a beautiful HST image of both the host galaxy where it happened and a little bit of the evolution of the source as a function of time. So some of the science results, which you know very well, is of course a measurement of the speed of gravity, the measurement of the Hubble constant, because we know they're standard sirens. I won't talk about, but there's lots of people in the audience that are expert here on the origins of relativistic outflows and gamma ray bursts, because these also came accompanied with a gamma ray flash. And I'm going to sort of focus on the evidence for the cosmic creation of heavy elements. And of course, there's some interesting work on constraining the physics of neutron stars and the deformability of them based on the gravitational wave source. So again, I wanted to point out that Robert did seminal work in pulsation theory, which actually led to the clear understanding of Cepheids and their use as distant indicators. Similarly, I think there's been incredible work on really understanding the gravitational wave signal, and as a result, our ability to use them as standard sirens. And as you know, the errors are relatively large, and these basically stem from the fact that we don't really know the inclination angle of the neutron star merger. So this is basically the determination of the Hubble constant as a function of inclination. So the first thing was, okay, we know the heating rate. Can we actually effectively compute the bolometric luminosity? The answer is yes. And here, basically, I'm showing you the heating rate for about a mass, so we can derive a minimum mass of about 0.02 solar masses. Remember that magic number of 10 to the minus 2 solar masses for neutron star mergers. If the rate is 10 to the minus 5, we expect about 10 to the minus 2. Of course, there's some efficiency here in turning that heat into light and the efficiency of energy deposition. But as you can see, the overall shape agrees relatively well with the heating rate. And of course, at late times, things are much more complicated, as you expect, and the material is becoming significantly optically thin. So if you assume the LIGO rate, that implies, with large uncertainty, it's a Milky Way rate of about 25 mergers per mega year. That's, again, these 10 to the minus 5 per event. So 10 to the minus 5 multiplied by 10 to the 10, you have about 10 to the 5 events that have occurred in the history of the Milky Way over the Hubble time. Yeah. That's more or less the goal that actually is in your body was, on average, made by that many neutron star mergers, which efficiently mix in the Milky Way. Our estimate for this event shows a total R process mass of about 0.06, and the cumulative mass of this is, a mere 10,000 solar masses of R process, and that's 10,000 masses. 10,000 solar masses is more or less the amount of R process that we see stored in stars. Yeah. So in terms of, can we basically predict that these systems operate robustly for the entire history of the Milky Way? It seems like on average we can get an order of magnitude result that the mass production rate is what we expect. Of course, it's only one event, and we want to see the diversity of that. Another interesting component was, are you absolutely sure that you produce elements between the second and third peak, where we know the abundance pattern is extremely robust? And so this is the spectra, and these are sort of the models that Dan Kaysen produced before the discovery. And you can see, or fit to the spectra, basically we have two models, one that had primarily first peak R process, which was very blue, and then a second model which had the required amount of lanthanide in the second peak, and this was extremely red. So from these here you have sort of if you look at the abundance pattern, sort of what we think the first peak came from, and then the second and third peak. What is interesting is actually from star to star, we see significant variation of the first peak, but the second and third peak are extremely robust. So from the spectra, we haven't identified a particular feature that says, this is the gold feature, because I explained to you, sort of the ocean of lines that they have and the fact that they're all broadened at 0.1c. But just by opacity arguments, we think that we detected incredibly complex atomic structure atoms, which are representative of these F-shell nuclei, which gives credibility with this argument that we have indeed detected the production of these R process elements. So this is sort of the model that we think. There's something in Nutristore mergers that is called sort of polar squeeze ejecta, which may be relatively blue. We think that gave rise to the peak. And then we had either the tidal tails or some later phase produce a significant amount of R process with significant elements between the second and third peak. And this is sort of the prediction of the modeling based on the prediction. So what I would say is, incredibly gratifying that given the level of ignorance that we had, we were able to make, relatively solid predictions of how these transients were going to look like, and that we got some validation. Of course, there's a significant amount of work to do and lots of open questions. And particularly, there's a lot of discussion about this blue component and whether or not it's radioactive in origin or not, and where it came from. So, there's significant amount of work to be done, and I think the field is converging in some of these questions. But what caused the electromagnetic emission? We saw this event also from non-thermal emission to thermal emission, from radio to the optical X-rays, and so forth. Do neutron star mergers produce heavy elements? It seems that that's the case. Are the source of all heavy R process elements? At least in the local universe, it seems to be the case. There's a significant amount of debate as to whether these sources operated effectively in the early universe. And interestingly, I think the physics of what happens to the merger remnant, did it collapse to a black hole? Was it able to actually survive? Did it produce a supermassive neutron star? All of these have deep implications on the different ways in which we can produce our process elements. And I'm going to just highlight a few. So I talked what I consider the most robust process, which is the tidal ejecta. That's, of course, guarantee. It's incredibly neutron rich, and it's actually shown to produce very effectively the second and third peak. There's these squeeze polar ejecta, which is basically you get material of very, very high entropy here in the merger interaction zone. So material actually shuts off in the direction of the pole where the pressure gradient is the steepest. That material is not as neutron rich, so the argument is it may produce only the first peak, and it's not able to go to the second and third peak. And then if these merger remnant collapse into a black hole with an accretion disk, the disk wind ejecta could also be a significant source of our process elements. In particular, there's significant amount of debate about how neutron-rich the material is, because of course it depends on the neutrino irradiation. Some of the advantages of the tidal tails is that they don't get significantly irradiated by neutrinos, while these ones do, and neutrinos change the neutron fraction. But here you have a huge amount of mass reservoir, so the argument that people are making is that the tidal tail ejection may not have been sufficient to actually produce the total amount of our process that we see. So as you can see, there's a lot of complexity, and it will be incredible, as LIGO starts detecting more of these systems with accurate positions, and we follow them electromagnetically to actually see the variety, which will depend on the mass ratio, whether or not you have a black hole, neutron star, and so forth. So we are just in the beginning, but it seems that at least we have the basic foundations in which to interpret this observational discoveries. So I hope I convinced you. And there's many aspects of things that I didn't talk about, how you make these two neutron stars so that they actually in spiral in less than a Hubble time. That's an active area of research. And of course, there the evolution is purely driven by gravitational waves. You can do the point mass approximation here, and it works wonderfully. Then you can talk about the merger dynamics, and there's a huge amount of physics, hydrodynamics, general relativity, the nuclear equation of state, and neutrino physics. The post-merger event is incredibly interesting after they collapse. And thinking about now not only hydrodynamics, but magnetohydrodynamics, in which you also have viscous stresses driving the material inwards and transferring the angular momentum outwards, and thinking about what sort of outflows they produce. I convince you that there's lots of interesting physics here in the nucleosynthesis. We have effective nuclear networks, but we're not able to completely explain the R process pattern exactly as that of the sun. So there's a significant amount of work to be done there. But at least what we find for many groups is that the pattern that we're producing is incredibly robust. We have, of course, radioactivity, and there's some interesting questions about nuclear decay chains, fission, alpha, beta, gamma fission, and thermalization, and how that energy is ultimately injected into the remnant and expanding. And of course, radiation transport with time-dependent spectral Boltzmann transport. And the atomic physics here is an area in which we really need to understand every single line energy, every single oscillation strength from these atoms, and especially at these lower temperatures, which is complex. So I'll stop there, and I thank you for your time. Yeah.
Great, thank you. Questions?
You mentioned having all of our process come from neutron star mergers. Can you comment on the europium to magnesium ratio in the Milky Way disk, and why europium seems to trace magnesium very well? Because magnesium is a common source. We expect at least a bit of the europium to be quite good.
Yeah. So we can go into detail. So there's three arguments I think that are being given that put into question whether neutron star mergers are effective, and I know you have contributed to some of them. So one, for example, is at this low metallicity, if you take two neutron stars and basically ask, how long it will take for them to merge, particularly because, the initial conditions that you can get closest is a helium star and a neutron star. That already puts a filter of about 100 million years or so. And the question is, after 100 million years, can you actually enrich the very low metallicity stars? I seem to think that you can, and we have some calculations that can show that, but there's a significant amount of debate of how effective that is and whether or not turbulent mixing is. Then you also see this magnesium europium trend that is actually decreasing, which is slightly disconcerting. And then the question, one of the arguments is, are we getting the magnesium to iron production incorrect? So for example, one possibility which you work on is that the iron content as a function of time by type 1a changes between the prompt channel and the delay channel. And that could help explain those gradients. But there seems to be that hints to the desirability of having something that actually accurately traces the star formation rate too. So sort of a prompt R process channel, which is what hints, as you were saying, with the magnesium to europium ratio. I don't know how much you believe the scatter being intrinsic in that particular case. Do you?
Yeah, I'm sure there's some intrinsic scatter, but it's just striking that europium to magnesium is quite flat over the last 0.5 to 0.7 decks between the sun and now.
I mean, every single simulation that we have done, cosmologically with neutron star mergers clearly show the decay, as you would expect. So having the flattening is concerning.
I'd like to understand the remnants after a neutron merger. So scenarios could be a black hole or a supermassive neutron star, and either one is interacting with a disk around it. Would there be another kind of gravitational wave signal that could be associated with the remnant itself? Of course, it'd be really low amplitude.
Yeah.
What would that look like?
Yeah, I mean, I think if you have to break the symmetry, and I think in that particular case, the quadrupole change is small, so you expect some decay. I mean, I would love to have high frequency and actually see the collapse into the black hole. That would be incredible. But yes, so you're right. You're going to have some signal, particularly maybe driven by the viscous instabilities. But I am assuming the amplitude is going to be tiny. Yeah, and it depends. I mean, for example, if you have a relatively massive black hole, the neutron star may just fall whole, entirely inside and get disrupted inside the event horizon, and we won't see any electromagnetic signature. So these new events, which could hint on a black hole and a neutron star, and the black hole is low mass, that will produce significant mass ejection in the tidal tails. So we expect these signatures to be relatively bright. In the squeeze, just because the timescales are very fast, because the expansion, you get such high entropy material that the freeze out happens very fast because just the expansion speeds are significantly fast. That's all. So even in that particular case, you don't have significant amount of neutrino irradiation, and it just has to do with the expansion timescale of the outflow. So you basically, you start producing first peak, you're going to go to second and third, and then basically your neutron flux due to the expansion just basically quenches, and then you're not able to go second and third peak. So the timescales do matter for the expansion.
Is iridium made by our process? Gold and platinum. But what about iridium?
What about iridium? I'm looking at, yes, I think it is, yeah. I have my... It is, yes. We can actually, I'll try to place it there because it'll be a challenge. I'm giving you my talk backwards.
Iridium in my work.
Okay, we can ask Evan to actually place it. Where is iridium?
I think it's
Right next to,
On the right side, no? On the,
right next to platinum.
you said on the right side of platinum.
Can you comment on how much uncertainty in the equation state affects the art process yield predictions?
Yeah, so what we're finding in general, I would say, especially in the tidal tail ejecta, it matters a lot to try to understand the amount of mass. But the initial conditions, if you ask basically what the entropy and initial density plus the thermodynamical evolution, very little. And in fact, what we find in the outer parts is that the temperature is actually not that important for the capture. I think for the rest of the merger, it starts mattering significantly. Particularly things like alpha particle recombination, I think about in the accretion disk and the neutrino irradiation there makes the determination of the initial YE very sensitive. Now, I mean, in the neutrino wind calculation, some of the uncertainties were that the material was not very neutron rich, and in that particular case, the entropy mattered a lot. But people have shown, even in very eccentric past, say like you have a collision of a black hole and a neutron star, and you just strip material and let it go, then that material also leads to a very similar robust R process pattern. So, and that's in some ways what you want. You don't want, if you want to have an incredibly robust pattern, you better not depend too sensitive on the initial conditions, otherwise you get into trouble.
Okay, well, if there are no more questions, Enrico is here tomorrow. His schedule is completely full, I think, from 9 a.m. till 5:30, but the last time I looked, there was a window of 5:30 to 6, if you haven't heard. Or you can ask him at the refreshments afterwards. So let's
Thank you so much. Yeah. Thank you.